Okay, well, it looks like it is the turn of the hour. It's 11 o'clock, so we're going to go ahead and get going. So thanks for everyone who's here for today's presentation called Laser Solutions for the Automotive Industry. Today we're going to be taking a look at a bunch of different lasers technologies, both for design and manufacturing, that really benefit a bunch of different automotive applications. My name's Shane. I'm going to be your host here today for the presentation, and joining me today is quite a large panel. We have a few people on the line from the different laser technologies we'll be representing today. So we'll go ahead and introduce everyone as we get going, but just to give you an idea of what's on slate. Now, because we're going to be having quite a few speakers, what we're going to do is we're going to walk through four different sections in today's presentation, and we're going to have a little mini Q&A after each guest speaker's presentation, and then we're going to have a large Q&A to wrap up at the end if you have any other questions. But let's go ahead and get going. So today, as I was looking over those who were signed up for today's presentation, I noticed we have a lot of people from a lot of different segments of the automotive industry. We have people here from OEMs, people here from EMS companies, people from the design perspective, people from the process and manufacturing perspective. And what's kind of nice is that LPKF, we have a lot of different laser technologies that we think really benefit certain automotive applications, everything from lighting to human user device interface, as well as things in the drivetrain. So what we want to do is highlight a little bit about what we have and how it can help you. A little bit about us, LPKF Laser and Electronics. We are a global company. Our worldwide headquarters is just outside of Hanover, Germany, and our North American headquarters, which is where we're recording the presentation today, is just outside of Portland, Oregon. We have six kind of main product divisions, and what we are, LPKF, we are a equipment supplier. So we sell systems of laser systems for a variety of applications. Now, the four we're going to be covering today are what you see on the bottom of the screen: laser plastic welding, laser structuring of 3D circuitry on plastics, laser depaneling, and then rapid printed circuit board prototyping. So that's kind of the order of today's presentation. To give you a heads up of what we'll be covering, we're going to cover these technologies through the lens of walking through an automobile and the different spots where we have applications. So the very first thing that we're going to get started with is a pretty exciting application, which is laser welding of taillights. So here, what's kind of interesting is there used to be an age-old debate in taillight design and manufacturing, is it form versus function? Well, the nice thing about laser welding is that it provides both. So now I'm going to bring in Dax Hamilton, who is the North American Laser Welding Sales Manager. Dax, we've talked in the past how laser welding has really kind of changed the game when it comes to automotive lighting. So just how has laser welding changed the game?
Yeah, so thanks, Shane, for the introduction here. Basically, there's a few main points in how laser plastic welding has kind of reshaped at least the lighting industry from this standpoint. Basically, it's allowed full 3D freeform geometry in the taillights. Let's just take this for example. You can take a look at our first laser production laser plastic welded taillight here for the Hyundai Equus. Basically, it allowed the designers to make full 3D curves, where in traditional with like linear welding and some of the vibration hot plate welding, some of this geometry isn't possible, especially where the curves drop away from normal planar.
Sure.
So laser plastic welding has allowed full 3D freeform curves because the robot can get in there and basically access any angle. Another big deal is basically laser plastic welding has allowed the geometry, the weld seam itself, to come right up to the edge of the light, so there doesn't need to be any glue tracks or masking or anything on the edges, so the designer basically can get the weld seam right up to the edge, get the light inside to come right as close to the edge as possible.
Sure.
And I think that's kind of a styling requirement for nowadays. Another key critical point is basically the style. So the laser plastic welding in itself allows a very, very precise joint to be created, and it also looks really, really well through the lens. So in the case of the Hyundai light here, the stylists actually use that as part of the styling of the car itself. And another point too is the process monitoring. With laser plastic welding, you're able to monitor several pieces of the process from a quality standpoint. The most namely is LPKF patented technology called reflection diagnosis, and this allows the machine to basically check for gaps or voids as it's welding. And so it can mark that in the system, and basically you can either go back and weld over that spot, or you can reject the lamp.
Gotcha.
So those are the most key critical points for laser plastic welding here.
Yeah, and that 3D design element of being able to work those weld seams right up to the edge and into the design itself definitely is a big factor that has definitely opened new possibilities for designers and for the manufacturing floor. Now, we talked a little bit about the aesthetics of laser welded taillights, but why don't you just walk us through now just what laser welding is and how it works?
Absolutely. So with laser plastic welding, we typically have to have 4 criteria that are met. Obviously, you have 2 pieces of plastic that you need to join together. The top piece needs to be transparent to the laser wavelength, and the bottom piece needs to be able to absorb the laser wavelength. Between those 2, we need a good mechanical connection so that we don't have any gaps or voids.
Sure.
And then we also need material compatibility. So typically most thermoplastics, like thermoplastics, are laser weldable to themselves. And then we need to make sure that our melt temperatures are the same if we go outside like thermoplastics. So for example, the laser passes through the transparent piece, gets absorbed into the bottom piece, and through heat transfer, melts and mixes the 2 materials together.
Gotcha. And then, like we saw with the tail light, basically any shape or any contour can be laser welded, right?
Yeah, virtually anything, any shape you can come up with, we can reprogram our scanning unit. We use a Galvo scanning unit with the 2D laser welding systems,
Sure.
and we're able to direct that beam in an XY pattern anywhere you want. With the case of 3D plastic welding, we're able to direct the laser head. It's at the end of a 6-axis robot, and we can get that in basically inside of any cube, in any point in that cube.
Gotcha. So once you are in the process, what type of joints can be created with laser welding?
Yeah, so there's basically 2 types of main laser welding joints that we see. The first is what we call a lap joint. It's basically just where 2 flat pieces of material are placed together. The laser comes in and fuses it in one pass. Quite common also is the T-joint. This can also be utilized in quasi-simultaneous laser welding, where there's a sacrificial weld rib or a portion of the material we need to melt down to.
Gotcha. And then, so maybe in case of the automotive lighting application we just looked at, that taillight for the Hyundai, do you know which type of joint was used for that one?
Yeah. In that case, we actually had a weld rib, so it'd be more of a T-joint style. So the lens actually gets mated to the joint itself and gets melted down a little bit to achieve a good hermetic seal.
Awesome. So then moving just beyond the specific tail light application, talk about in general some of the benefits that laser plastic welding provides automotive applications.
Yeah, definitely the biggest one of the biggest benefits to laser plastic welding is the joints are clean and it's precise. So basically, with traditional welding styles, plastics joining styles, ultrasonic, for example, you're rubbing 2 pieces of material together and you're getting some particulate escape out of that weld process. So definitely it's very clean, very precise. We can control the laser exactly where we want it to go with very little heat affected zone. So if you have sensitive components inside or outside the weld seam, you don't want something getting melted or damaged inside or outside, we control that beam right exactly where we want it to go. A big deal is process monitoring. I think we covered a little bit of that before with the 3D welding. Process monitoring is huge. We're able to measure the collapse of the as the parts weld together and ensure this good hermetic seal. We're also able to check some of the other functions of the weld. So as the heat curve is one of them, we check that with a pyrometer, and we're able to send feedback to the machine to either raise or lower laser power to keep it within a specific process window. And we're also able to do one other form of process monitoring called burn detection, where we can sense surface burns or anything happening to the surface of the part where a part might need to be rejected from a customer. We can also integrate laser plastic welding systems very well into full-on production lines with automated loading, whether it be conveyor belts or robots, pick-and-place systems. So laser welding systems are very adaptable for integration lines. And overall, we're able to shorten some of the cycle times. Laser plastic welding is a very quick process, quick and clean. So overall, there's quite a few benefits, as you can see here.
Gotcha. And then you had mentioned when you were talking about putting 2 plastics together and how laser plastic welding works, looking over a list of sort of common plastics for automotive parts. Walk us through that really quick.
Yeah, so basically, like I said earlier, most of the thermoplastics, like thermoplastics, are laser weldable to themselves. Quite common in the automotive industry, obviously, are the different nylon grades, the PA6, PA66, 12s. The POM, which is an acetyl resin, this is quite common for fuel applications. It's very resistant to chemicals. PBT is quite common in sensors. PCABS, very, very common, very inexpensive material. polyethylene, PEs, as you see there below. Also PMMAs, which is acrylic. These are quite common for lens applications and,
Sure.
and so on and so forth.
Gotcha. So speaking of all those different types of applications, let's walk through just a few more laser welding applications, kind of show what's already out there in production right now.
Yeah, so basically, as you can see here, as far as the sensors go, there's, I think, over 100 sensors in a car today with all the different electronics and different systems that need to be monitored. They're anything from transmission sensors, oil pressure sensors, positional sensors, electromechanical type sensors.
Backup cameras.
So backup cameras is a big one. So basically, anywhere you need to store electronics and protect it from the outside environment or any sort of chemicals that would interfere, you're going to see laser plastic welding involved in these types of sensors.
Gotcha. And then I like this application, this water level sensor down there on the bottom, because it shows that when we're talking about a laser transmissive plastic with a laser absorbent plastic, it doesn't necessarily mean the plastic is clear.
Correct, and this is kind of a common misconception with laser plastic welding. The bottom line is that with the transparent layer, we just need to be able to pass that laser through the material. There are a lot of pigments and dyes that our compounders, the plastics compounders, can add to these plastics to make them appear black, green, blue.
Sure.
It really does not matter. It just needs to pass that specific wavelength of laser. And in our case, most of the time, it's at 980 nanometers.
Gotcha. So looking at a couple more component covers really quick. So here you can see the CV gator on the top left, which, again, talking about fusing together different types of plastic. This is a hard to soft weld, which is a nice achievement. But I know you're a fan of the radial welding process. So on that valve on the right-hand bottom, describe to us radial welding.
Yeah, so basically where you have a check valve or a round ball inside of a part that acts mechanically or maybe in shafts or different things, motorized applications, a lot of times we'll see radial type of joints. So basically the designer will create an interference fit between the two parts because we can't really get a clamping force on these. And basically we'll direct the laser around this part via mirrors, or we'll take the part in some cases and actually actuate it or spin it as the laser is being fixed. So this is quite common. We see this quite common in sensor applications.
Gotcha. And then one thing else I wanted to show really quick before we jump into Q&A was moving from, away from the drivetrain and under the hood is this interior application right here.
Yeah, we actually see quite a lot of what we call a Class A component, which is visible to the user or the driver of the car.
Sure.
In this case, it's an instrument cluster. This is basically a legacy product for laser plastic welding. Basically, we've been doing these for quite some time. And inside, obviously, there's light guides and electronics and the clear bezel that goes over the top. And this is a very, very good application that lends itself well to laser plastic welding.
Gotcha. Awesome. Okay, so that kind of wraps it up for this portion of the presentation as far as laser welding. I'm going to have Dax hang on for just a second, and we're going to jump into a Q&A. So if you guys have any questions about any of the applications we've covered here or questions about laser welding in general, Dax actually works pretty extensively with our automotive clients. So we're going to have him hang on. Dax, while we're waiting for some questions to come in, I want to ask you about prototyping options with laser plastic welding.
Yeah, so definitely here at LPKF in Portland, we basically have a full-scale application lab. So we can do material testing, we can do prototype tooling. We have the capability with local machine shops to build basically prototype tooling and anything we need to develop and test your parts for you. Basically, one of the benefits to LPKF and where we differ from our competition is that we provide full turnkey support. So we start not only along at the beginning of the design phase, we can work with you on your laser welding joint design, we can work with you on material selection, and work on that balance between what you need for your functionality of your part or your styling versus what works best for laser plastic welding to ensure you have a 100% guaranteed good laser plastic weldable part. We also basically, like I said before, we can work on develop prototype tooling so that we can weld your parts and give you functional parts to test. Once the process goes forward and you decide to put this into production, obviously we supply the equipment to do this. And then we also have a robust service plan to support the equipment when it's in the field and in production.
Gotcha. Awesome. So it looks like we explained everything really well because we don't have any questions yet. So Dax, thanks for joining us today.
Thank you, Shane. Appreciate it.
And if you want to hang around for the later Q&A, that'd be nice, Dax.
Excellent.
Thanks. All right, so coming up next, we're going to talk a little about, we're going to kind of stay inside the car, so to speak, and move to our next application, which is this steering wheel molded interconnect device. And what are we talking about with this? We're talking about laser structuring of 3D circuitry directly onto plastics. So this is a pretty interesting application, but here I'm going to bring on Stefan Schmidt, president of LPKF, who's a big big proponent of our LDS laser direct structuring technology for 3D circuitry. So Stefan, essentially what we're looking at is a molded interconnect device, but what is a molded interconnect device?
Yeah, thanks for having me on here, Shane. A molded interconnect device is a device that really combines a lot of different functions into one piece. And as you see here in this little graphic, just to show this a little bit, it really combines a circuit board or a circuit carrier, a housing, a connector, and a wiring harness all into one piece. So we basically put circuitry and connectivity on a plastic device and basically make it a bit smarter.
Gotcha. And then the big thing I know you've mentioned is like the whole 3D revolution kind of that this allows. So
very true. And most of the circuit design in the past really revolves around a two-dimensional item like a circuit board or even a flex circuit that's born as a two-dimensional part, right? Now, as we start to put circuitry on plastic parts, you really break those molds of the two-dimensional world and go into the three-dimensional world and really start to have circuitry going up the wall, so to speak, and we can really use that three-dimensional space in a different way.
And then in the case of this application, this used to be like a PC board kind of inside there, but then they built it right on that 3D cover.
Exactly. It's good. It's a good way to show here that there's a part that's already in there and it used to carry a circuit board. Why not take that part and put the circuitry right on it? So.
Gotcha. So how do you create these magical devices known as MIDs?
Yeah. So MIDs are made in a process, in a three-process step. Basically, starting out with the first process, just injection molding a plastic part. Now, this plastic is molded with a special plastic that has a catalyst built into it, and we'll get to this in just a little bit to explain what happens inside the plastic. So again, standard single-shot injection molding is the first step. The next step is a laser activation process. And this is here now the part where we will decide where the metallization will happen. So what happens on the inside of the part is the plastic, again, is doped with what we call a metalloorganic complex. It's a metal that's packaged in an organic packaging and in its native form being inactive. So in other words, it doesn't plate in the initial molded form. And you can see little graphics here on the upper right side of the screen that shows basically this yellow part is representing the plastic resin, and the black little dots in there basically is a catalyst compounded uniformly throughout the plastic material. Now we're going to start hitting it with a laser beam, and now basically the magic happens. We're opening up the organic packaging around the metal atoms, and now we have the metal atoms exposed, and only in those areas that we have touched with the laser here. And that really allows us to create the selective metallization only in those areas, versus everything else stays non-metallized. So again, we have the three steps: injection molding, then laser activating for the selective metallization, and then the entire part will be immersed into an electroless plating process, and then we grow the metallization only in the areas that have been exposed to the laser energy here.
Gotcha. So then we're kind of talking about two things when we're talking about creating 3D circuitry on thermoplastics. We're talking one about the parts themselves and then one about the process. So what are the benefits of MIDs in general? Yeah,
so MIDs, and as we talked a little bit about this in the beginning, MIDs really allow us to go from 2D to 3D. Again, the circuit boards are all two-dimensional parts, and really our thinking revolves around a two-dimensional world here. Going into the 3D world allows us to put circuitry in areas that we really haven't explored before. In most cases in the past, a housing is a housing, but it's not a circuit carrier. So now we can use the walls and the bottom of a housing to put some circuitry on it, or put some antennas on it, put some connectivity on it. So we can really start, to design parts very differently. Also, by making these molded parts smarter, we can really reduce the part count. We can put more components. We can put components on it, connectivity on it, instead of just having it as a housing itself. And then, of course, once we combine all these things together, this is actually an incredible weight saver. Circuit boards itself, it may not appear like much, but they are fairly heavy items. And if we have a plastic part anyways, and we can put some circuitry on it, we can really save some weight, which especially for the portable applications or for automotive applications, weight saving is always a great thing.
Gotcha. And then not only does you're reducing components, not only does that save space and you reduce your weight, but it also helps reliability because there's kind of less things that can go wrong.
Exactly. We have a reduced part count because and that really helps reliability altogether.
Gotcha. And then so what are the benefits of creating a molded interconnect device with this sort of laser structuring?
Yeah. So we talked about the laser direct structuring technology here a little bit in context of this molded interconnect devices, and laser direct structuring again is creating those molded interconnect devices all based based on laser technology. And really what it does, it allows us a very simplified production process of the parts itself. Again, we only use a single-shot injection molding process. So again, there's no limitation on the molding process itself, and it opens up a wide range of manufacturers for this. The other part is that it really allows a very high complexity of the circuitry itself. Since the laser beam now defines what the circuitry looks like, we are not a function of any kind of molding process there. So that allows us a lot more design liberty for the process, and then therefore really much higher resolution features, because we can create very small long lines on parts versus if you use traditional two-shot molding or embossing processes, we really wouldn't have that possibility. And then the other process, or the other step in the LDS process that's really attractive is LDS technology allows prototyping through mass production in the exact same technology. So there's no big step in that. So that really helps to design a part and come up with a basic idea, then refine a little bit, and then continue to use the same technology again into a full-blown, high-volume mass production environment there.
Gotcha. And then you were mentioning the LDS grade sort of materials that are doped with the special plastics. So what are these LDS materials look like for the consumer, and what plastics are available?
Yeah, so LDS grade materials, again, are plastic materials that are doped with this metallogenic complex, or the catalyst, as we call it. So again, if you would use a standard plastic material and would start hitting it with a laser, you still don't create a selective metallization process. So again, you need to use a specific resin type. However, there's a wide variety of resins, plastic resins available in this LDS grade, in this so plastic with the catalyst added to it. Most commonly used in the automotive industry, probably the nylon grade materials like a PA66T or PPA. We see also some applications with PCBs, a stronger material and lighter material, but lower temperature. We see LCP applications or PBT, especially for very small, high temperature applications, so sensor carriers. Yes. So again, there's a wide variety of plastic materials available there.
And then is it hard to find these LDS grade materials?
Not at all. So there's a lot of manufacturers, and you see just a few of them here on the screen that provide LDS grade materials. So if you have a certain material that you use already and you're interested in going, maybe putting some circuitry on it, please talk to your resin manufacturer, and it's most of them probably have an LDS grade material of what you use currently available. So.
Gotcha. Awesome. So then let's jump back into applications. So here, this is a great example of what you were mentioning when it comes to reducing components and kind of streamlining everything.
Yeah, exactly. This is an application here for a steering wheel wiring harness, and you see on the left side what a steering wheel wiring harness typically looks like. There's wiring harnesses, there's connectors, then there's button assemblies that go on top of this. So there's a lot of parts involved in that, and of course everything in a very three-dimensional space, because in the end this has to be used for the human interface, and we humans aren't built two-dimensional, so we're going to start going three-dimensional here. And now this part, the LDS part, or the MID on the right side, you can see is a three-dimensional part that combines wiring harness, connectors, and the button assemblies and everything all in one part, which then in manufacturing would be put into the steering wheel. And so it reduces assembly costs, it reduces weight, reduces the part count, and it really allows us a three-dimensional approach, which really wouldn't be able to do with a standard circuit board.
Sure. And then another huge area of application for laser direct stretching molded interconnect devices is antennas. And so talk to us about creating antennas with LDS and how that relates to the automotive world.
So antennas is really the most successful application of the molded interconnect device today, and most of us probably have a molded interconnect device already in our pockets in this very moment in our cell phones. And cell phones are a very good application for this, because they're limited in space, but we want to have more and more wireless functionality in there. So what can we do? We just have to take those antennas and kind of fold them around curves and corners, and we put them in all nooks and crannies, because the phones can't get much bigger than they are, although some phones are trying to push that right now. So in the automotive world, we have the same application. We have more and more areas, true three-dimensional areas that we can use both on the inside and the outside of the vehicle for wireless connectivity, both for cell phone, GPS, Bluetooth, everything in between, for connectivity from the inside to the outside of the car. Since we're in the car, we're not in the best cell phone environment. Sometimes we want to connect this to the outside world, so we can bridge that too. So again, we can use a variety of items here and take those antennas and really put them in a three-dimensional space, rather than having to deal with very, very long, large devices, which are sometimes hard to hide.
Gotcha. And then I wanted to talk about something here, Stefan. Talk about the design freeze in working with antennas and kind of the advantages that provides, especially because cars could have many different antennas, GPS, Bluetooth, cell, so...
Design freeze is a great aspect here for those MIDs, and especially for those laser direct structured MIDs. So antennas, again, every antenna designer probably will share this experience. The longer they can, tweak the design, usually the better performance they can get out of this. And LDS is a great technology that lends itself for basically late design freezes or even design optimizations throughout the process, because in this process the circuitry is disconnected from the molding of the part itself. So you basically mold parts, and then as you go along continue to improve your antenna design, and then have your design freeze much later on, rather than doing this early when you maybe have your mold design, because the circuitry is really only a function of the computer process of laser structuring on the part itself.
Awesome. And then our final application before we jump into Q&A here. This we talked in the beginning, and we kind of tried to stress the 3D element of MIDs, and this really exemplifies the 3D revolution when it comes to MIDs, doesn't it? Yeah.
So earlier we saw a steering wheel for a car. So again, fairly large part here. Now, if we go into a motorcycle, now we have to do this in a much smaller scale. So that's a fantastic application here to really go three-dimensional. Again, the motorcycle here has a lot of functionality on the handlebar, many more than they used to have back when I rode a motorcycle many years ago. Here, but again, the space is three-dimensional, and we have to reach it with the thumb only. So one finger has to do all these things like cruise control and whatnot. So having a part that really wraps around the handlebar, has the button assembly on it, has the connectors in it, all these things into one three-dimensional part, that's a great application to really embrace this three-dimensional space. And we can all imagine doing something like this with the standard circuit board, or even with the flex circuit board, is extremely challenging and would require a lot more parts and more cost to it too.
Gotcha. Awesome. Okay, so Stefan, we're going to have a little Q&A here, so I'm going to give the attendees and the audience out there a few moments to put in their questions, but while we're waiting to see if we get any questions, I wanted to ask you talked about laser direct structuring, being able to handle the whole process from R&D through mass scale production, but specifically talk about that R&D options. What prototyping options are available for laser direct structuring?
Yeah, for laser direct structuring, again, as we initially said, LPKF is an equipment manufacturer, and we just recently launched a product range that is really designed for designers. It's easy to use, smaller type equipment that can be used in the lab to basically create three-dimensional circuitry parts right away on the spot. So the combination of a small, easy-to-use laser system and small in-house plating solution really allows pretty much anybody to put three-dimensional parts together.
Gotcha. Awesome. And then again, let's see. I think we're good on questions. I think we are excellent presenters. Is I think what we're
Thank you.
From this. So no, Stefan, thanks for stopping by for this.
Okay, great. Thanks, Shane.
Awesome. Great. So we're going to kind of shift back from the sort of parts for 3D capabilities, and we're going to kind of shift gears a little bit. And what we're going to talk about is stress-free processing of optical components. And what we're specifically referring to when it comes to this is depaneling PCBs that have been populated with mounted components, specifically sensitive optical components. So UV laser depaneling is a great area of application when you need to protect your components. So I'm going to bring on Mirella Orlovsky. She is a fellow alumnus of Portland State University like myself, where she earned her master's in electrical engineering. So Mirella, talk to us about laser depaneling when it comes to this factor of not wanting to harm your sensitive components.
Thank you, Shane. So let's move on. There we go. There's my image. So the image you guys are seeing here is actually a magnified lens, a backup camera lens. So this particular lens is, of course, part of a printed circuit board, an FR4 62 mils thick printed circuit board. And the part on the right was the panel with the UV laser, and the part on the left was the panel with a conventional router.
Sure.
So what you see here is the lens on the right has quite a bit less or really minimal debris,
Sure.
which in a case when you have a lens of a printed circuit board is extremely important.
Mm-hmm.
So not only are you able to utilize UV lasers to the panel parts with no debris, not damage your parts in this case, you're also able to eliminate some post-process cleaning.
Gotcha.
And save money this way as well. In fact, the customer whose lens this is or whose printed circuit board this is had something like 3 cleaning stations that they used after the routing process
Sure.
because there's just dust everywhere in the air. Once they switched to the paneling with UV lasers, they eliminated every single one of them.
Gotcha. So not only are you not damaging that camera lens for the backup camera, but you're limiting the post-process cleaning. And what's kind of cool about this particular application is not only was this, because sensitivity is of the utmost importance for these types of safety features, not only was this used for stress-free minimal debris laser depaneling, but the cover for this was actually laser welded, which that's pretty neat. So, Marilla, let's talk in general about UV laser depaneling and the benefits it provides.
Yeah, so really, for those of you that don't know what UV laser depaneling is, it is an alternative to some conventional depaneling methods like
Sure.
routers or pizza cutters or die punching and so on. So in addition to minimal debris that we just saw with the backup camera application, one very important advantage is the fact that UV laser depaneling doesn't put any mechanical stress on the board when you're cutting it. So really, there's no vibration that can damage some critical components on the board.
Sure.
Another very important advantage is that you're really limiting or minimizing or completely eliminating your thermal stress, depending what type of material you're working with and its thickness. You can also cut virtually any PCB material like polyimide, FR4, Rogers, LTCC, fire ceramics, and so on. So it's a very versatile machine. And the great part is you have no shape limitations anymore. With some older methods like pizza cutting, which is still widely used, you're only able to cut straight lines. When you're working with a laser, you have a 20-micron beam, and you can really cut any shape you can imagine.
Sure, gotcha. And then moving on, the benefits of this no mechanical stress and limited thermal stress is the material diversity, right?
Oh, absolutely. So what we can see in the industry is that there's a really wide variety of materials that people use. Some we have flex manufacturers and rigid flex and so on, and then fired ceramics is another extremely popular material.
Sure.
And a UV laser can process them all. They can cut them and drill them and ablate them and so on.
Gotcha. And then you mentioned flex circuits, which is a huge area of application. In a way, almost UV lasers are like almost designed for cutting flex circuits in a way. So talk about the difference between UV lasers and other lasers when it comes to cutting flex applications.
Yeah, you were right, Shane. Actually, UV lasers were designed to cut flex circuits. That was the primary application. So because UV lasers use typically very little power in comparison to, in this case, a CO2 laser on the market, they really, really perform well when it comes to depaneling really thin films.
Sure.
So in this case, what we see is a 120 micron thick polyimide, and the one on the right was cut with a UV laser, and the one on the left was cut with a CO2. And you can see the difference in the thermal effect on the material. On the right, it's minimal. And the reason for that is not only are we using small power to start with, we're also able to control our parameters really, really well and really tight, depending which material we're processing.
Sure.
So even if we have a laser with 6 watts or 10 watts of power, we may only be using 3 watts to depanel 125 micron thick polyimide. So that's the great part about them is that flexibility, where you can go from flex to rigid with the same machine.
And then staying on the subject of flex circuits, we often like to joke that it's like a knife going through butter. And this is a huge advantage for people in the automotive industry because, there are flex circuits all throughout cars.
Yeah, it was surprising to me quite like how many flex circuits are in cars. So they can go anywhere from underhood controls and fuel pumps to GPSs and GPS systems and AC systems and so on. So, I mean, really, when you're looking at the electronics industry today, parts are getting smaller, they're getting thinner, the shapes are getting more complex, and now you have requirements that you didn't have before, like you have to eliminate the thermal stress, or you cannot have any debris on your parts, and so on. So the depaneling portion and the UV lasers are becoming more and more important in this industry as well.
Gotcha. Awesome. So here we'll just run into a Q&A, and then while people are maybe putting in their questions about UV laser cutting in regards to depaneling, Marilyn, I want to ask you. You mentioned CO2 lasers and UV lasers and different types of lasers, and talk about the difference between them when it comes to cutting copper.
So that's another really nice benefit of the UV lasers is that, for example, CO2 laser was also pretty widely used for the paneling in the PCB industry. However, one of its negative points is that it's not able to cut through copper. And often you find yourself in a situation where you may be cutting a multi-layer board, and you're not only cutting the substrate portion. You have to cut through, most of the time it is copper. You have to cut through some sort of a metal, and UV laser is able to do that without an issue.
Sure.
So because you can control your parameters, you can cut, either only through copper and then stop at a substrate, or cut through a multi-layer board with no problems.
Awesome. Great. All right, Marilla. Well, it looks like no questions have come in, so we're going to go ahead and roll on to the final portion of today's presentation, and we're going to talk about rapid prototyping of printed circuit boards. And this may seem like, well, how does this apply to the automotive industry? But, in the automotive industry, R&D is huge, getting things right before they go into production. And because you have new models, new peripherals, new electronics components coming out each and every year, sometimes multiple times a year, reducing time to market is very important for automotive R&D. So, what rapid prototyping allows is a more competitive R&D department. So what we're talking about when we're talking about rapid prototyping printed circuit boards is in-house mechanical milling or laser processing of circuit etching and creation. And the great thing is like most single or double-sided boards can be milled or etched within an hour, and that really allows for a quick turnaround and innovation. This is used in many automotive settings, and we have quite a nice base of automotive clients when it comes to this. There's a Formula One racing team in Germany, and they use a milling system to test, verify, and modify sub-designs while they are, kind of fine-tuning the race car to get it ready for race day. And so, in this type of setting, when you are trying to optimize performance for the board in the car, being able to make sure that that's optimized at peak performance before it goes out onto the racetrack, or in the case of a supplier, before it goes out into production, is huge. And then kind of moving away just kind of from general sort of engine components, Denso, who makes a variety of different components for cars, everything from wiper blades, which don't have circuits, to other sort of RF sensors. They are able to use their PCB milling system as well to prototype, and not only prototype, but to make revisions and get your designs dialed in before you get into production. And then I wanted to grab Rory Grondin, who is our rapid prototyping sales manager for North America. And I mentioned RF sensors. So talk about, getting beyond kind of the standard sub-circuits, test circuits on FR4. Talk about the capabilities of in-house prototyping for the sort of new horizon on the edge for cars, which is all these sort of sensors.
Yeah, well, thank you, Shane. It's great to be here. And, this is a division of LPKF that goes back to our origins. Over 37 years where PCB prototyping equipment was created so that engineers could get their boards faster and make changes quick and on the fly to, really improve the time to market on their products.
Sure.
And what we've seen and what LPKF has done is we continue to innovate with our machines, developing new features that save time and money on the applications. And this allows for current applications and future projects to really have a solution with the products that we offer. And what we're seeing is a lot of future innovations that are going to be necessary with the automotive industry. Mm-hmm. Specifically, there's new legislation for car-to-car communications and accident prevention that that we're seeing for big initiatives, and that might be kind of a healthy, hefty goal, but it's something that can be met and is in with technology that's already in place, and we have solutions to help labs actually develop that for the future. So basically being able to work with any material from standard circuit boards to flex and even fired ceramics is really the focus of our prototyping division, and it's something that we definitely have several solutions for.
Gotcha. Awesome. And then, so when we're talking about mechanical milling, laser processing, what's available?
Yeah, well, LPKF and mechanical milling machines have advanced over the years. A lot of features that have gone into those. And here you can see one of our standard milling machines on the left, which now includes fiducial camera, automated tool change, automated tool depth setting, and really allows you to work with some of the most common materials, FR4, fiberglass woven substrates, even Rogers substrates for high-frequency applications for the sensors, antennas and filters, microwave filters, and so on. And with those machines, they're great for prototyping. They can mill a board, again, as you said, in under an hour, in many cases, in fact, in minutes for small designs, and go down to the 4 mil trace and space range. So something that LPKF prided themselves and founded the company on, and has continued to dedicate resources into making them easier to use, faster, more precise, and friendlier for the operator. And then the next system you see here is kind of what will tie in with the last one, with the laser processing, but we've combined the capabilities of laser etching with mechanical milling. And there's some benefits with that, really for the smallest and more high-density interconnect devices and the demands that are coming out with circuit boards getting smaller for the tight spacing, which is obviously of big importance in automotive. So you can go smaller with your trace and space, using a laser in this case to do the finest isolation, but then using a mechanical tool, carbide tooling, to drill, cut, and do larger areas of copper removal or metallization removal for those parts. So your speed increases by allowing you to do more of that application and still only needing one machine. And so that's just an incredible advance that we've had on the systems. And when you take that one step further, you get to laser processing. And laser processing, we have a couple different units, an IR laser and a UV laser, that are designed to remove the surface metallization extremely fast, on the range of 4 or 5 times faster than mechanical, which gives you actually cleaner edges and less effect on the substrate for a lot of materials, and opens up the door to work on materials like fired ceramics, where mechanical milling would not allow for that to be processed. And even flex applications, we're seeing some advances and additional materials being processed with the lasers every day. With that, you can go very, very small with the laser, either having a 15 or 20 micron, 25 micron beam width, and the speed is incredibly fast, as I mentioned before. So that's kind of a brief history of the past and what we've planned for with the future, the tools that we have available.
Gotcha. And then talking about the speed on the laser processing, I know that not only is R&D possible, but in the case of like smaller RF sensors and filters, like we were talking about on the last slide, some companies are actually starting to do their own in-house production with that, right?
Absolutely. In fact, one contact is actually doing upwards of 500 custom filters per week using just the laser, and the lasers actually give you another benefit where they can actually drill and cut the materials depending on the laser, with very small drill holes and like Morella mentioned before, just extremely clean edges, which relates right into production when they need systems for that in the future.
Sure. Awesome. Well, that's our quick little plug for the RP at the end. Again, it's hard to point out a specific application with that because a lot of its use is in R&D, and the nature of that kind of limits what we can share. But it's a great tool. And while we're waiting for some questions to roll in, I know one exciting thing is a lot of times in cars, when it comes to kind of consumer-facing devices, especially in regards to radio and different electronics inside the car, it's moving to touchscreens now. And one exciting thing about the lasers is it can actually kind of work with the sort of transparent conductive oxide sort of glass touchscreen materials.
Yeah, it's kind of a fun, more of a side application that the UV laser offers you, is being able to remove I2O, from glass to do touchscreen development. Sure. So more of a production application that's already just a standard process. But if somebody wanted to do research and development, that they could use the UV laser.
And that's really cool. All right, Roy, we're going to head into the conclusion now, so thanks for stopping by.
Yeah, thank you, Shane.
So to kind of recap, we covered a lot of different technologies for a lot of different applications. We started off talking about laser plastic welding, how that's kind of really changed the game when it comes to automotive lighting, and then how it is a sound solution when you are working with components that are going to be in harsh automotive environments or covering sensitive parts. Talk a little bit about the 3D revolution when it comes to the human user interface, and how structuring circuitry directly onto plastics really helps that out. We talked a little bit about laser depaneling, how that really benefits your sensor applications when you have optical components that can't stand to be damaged, or you don't want to spend a lot of money on post cleaning. And then we just talked about rapid prototyping. So I was going to launch a poll, if you don't mind answering this. Which of these technologies interests you the most? Maybe you see an area of application that maybe fits your sector, or maybe you just like more information about one. I'm going to go ahead and launch the poll, and then we're going to kind of jump into a general Q&A. So if you just hang tight, we'll go ahead and have the poll open for 30 seconds to a minute, and then we'll see what questions we get in. All right, so I'm going to go ahead and close the poll for now and get back to the presentation. I just wanted to thank everyone for attending today. We were pretty excited about this webinar to be able to, we really think we have some valuable things going on for the automotive industry, and so it's nice to see the wide variety of people who are able to attend. We're going to go ahead and jump into Q&A. So if you had any questions that you had maybe from the beginning of the presentation, maybe you came in late, go ahead and get them in now. Up here I have contact info if you do want to reach out to any of our individuals that can help you kind of look at, experimenting with and implementing some of these laser technologies. This will be up here on the screen now, and then I'll also email this out later. I'll email the slides out later with this information. But we'll go ahead and jump into Q&A, and I'm going to hold on just for a second to make sure we can get all questions in. Okay, I do have one question coming in from John, who wanted to talk about the 3D MIDs and specifically in regards to soldering components onto them. So if you could touch on that, Stefan.
Yeah, Shane, this is a very, very common question about this, and of course very valid. If we use a plastic part and start to make it behave like let's say like a circuit board in many ways, of course, the problem comes up: how are we going to get the components on there? Sure. And of course, plastic parts are typically not as high temperature as a standard in a FR4 circuit board would be, or a flex circuit. So there's a variety of plastic grades available that we talked about earlier in the webinar, and some grades are higher temperature than others. So if a part is designed and there's supposed to be components soldered to it, then typically you should choose a plastic material that has higher temperature grade. For example, the nylon grade materials are pretty common for those in automotive applications, or for very high temperature applications, typically an LCP material of that neighborhood. Again, those materials have high enough temperature range that they can be used for standard soldering of components directly on it. While we're at it, we might want to talk about assembly as well. Sure. If we're starting to use assembly on a three-dimensional part, it's important to consider that your assembly process is compatible with this three-dimensional world. Many standard pick-and-place machines are designed for again, flat circuit boards or flex boards that are, again, still in their two-dimensional stage. But there's a variety of pick-and-place machines and service companies that are capable of handling three-dimensional parts. So again, this is just an important part of consideration once you start to assemble components on a three-dimensional molded interconnect device, to make sure you select your vendor accordingly.
Awesome. Thanks. All right, so it looks like we actually don't have any other questions coming in, so I'm going to wrap things up here. So once again, thanks everyone for attending today. We will send out a recording of today's presentation in case you came in late or want to review it, as well as the slides. So once again, on behalf of all our presenters here today, Rory, Dax, Marilla, and Stefan, thanks for stopping by.